Hi everyone. We're now going to look at the unit circle approach to trig. The unit circle approach is better for angles outside of quadrant 1. It's much better for analyzing quadrantal angles and also angles in other quadrants. Okay, so here's the setup. Consider an angle in standard position, meaning that the initial side is on the positive x-axis. Here's our angle theta. Now the terminal side intersects the unit circle here at a point. This here is the unit circle centered at the origin. Now this point of intersection, it's very convenient. The x-coordinate of this point gives the cosine of the angle, and the y-coordinate gives the sine of the angle. It's very convenient. Oh, and an extra bonus, something that many of you didn't know, the slope of that terminal side is tangent of theta. Tangent is slope. That's a big breakthrough I got from a student one time, and it's still stuck with me. It's a great way of looking at tangent. Tangent is slope. Now, why are these things true? It really comes down to SOHCAHTOA. So over here, we have our angle theta. Sine of theta, SOHCAHTOA, sine is opposite over hypotenuse. Now, for this unit circle, the radius is 1, so the hypotenuse is 1, which means that this side here has to be sine of theta, because sine of theta is opposite over hypotenuse. This has to be sine of theta. This is the y-coordinate of that point. Cosine of theta is adjacent over hypotenuse, so this better be cosine of theta. This intersection point has an x-coordinate equal to cosine of theta and a y-coordinate equal to sine of theta. Oh, and by the way, what's rise over run? It's slope. And what's sine of theta over cosine of theta? It's tangent of theta. Tangent of theta gives the slope of this terminal side. I'll type that in. Slope equals the tangent of theta. X-coordinate is cosine of theta. Y-coordinate is sine of theta. And please make sure not to mix these up, because we usually study sine first in trig. So remember, that's not x, it's y. That's a big source of confusion. Tangent is slope. Now, remember, the x and y coordinates on the unit circle are going to fall between -1 and +1 on both the x-axis and the y-axis. And that corresponds to the fact that both sine of theta and cosine of theta can pick up all real values between -1 and 1, and only those values. In particular, the closed interval from -1 to 1, that's going to be the range of both of these functions, sine and cosine. Tangent, however, is slope. Tangent can be any real number, because you can get 0, positive slopes, 1,000, 1,000,000. Slope could be negative as well. The slope is negative over here and over here. We'll talk about that. The tangent can also be undefined, like at pi over 2. The range for tangent is all real numbers. We'll talk more about range later on. All right, now it's time for the table. And you should be able to write this out on a piece of paper in a minute, easily within a minute. There are nice patterns for the special trig values. Let's look first at sine of theta. Here's the pattern for these key special angles between 0 degrees and 90 degrees. The key special angles are 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Remember, we got these from the special triangles. And these are the related quadrantal angles in quadrant 1, the close by ones. In radians, 0, pi over 6, we skip pi over 5, pi over 4, pi over 3, pi over 2. All right, here's the pattern for sine of theta for these angles. It goes root 0 over 2, root 1 over 2, root 2 over 2, root 3 over 2, root 4 over 2. And you can simplify these. Root 0 over 2 is 0. Root 1 over 2 is 1/2. Root 2 over 2 and root 3 over 2 are both simplified. Root 4 over 2 is 2 over 2, or 1. So these here are the values of sine of theta for these special angles. So sine of 0 degrees is 0. Sine of 30 degrees is 1/2. And that's a really good thing to remember. So if a physics professor asks you, and I've heard this done before, if a physics professor asks you, what's the sine of 30 degrees? It is 1/2. That's a good thing to remember. Sine of 45 degrees is root 2 over 2. Sine of 60 degrees is root 3 over 2. Sine of 90 degrees is 1. Now remember, sine of theta corresponds to the y-coordinate of this intersection point on the unit circle. As we increase from 0 degrees to 90 degrees, as we increase, I'll write this in orange, as we increase from 0 degrees to 90 degrees, what happens to the sine value, or the y-coordinate? It increases. It goes up from 0 to 1. As we go from 0 degrees to 90 degrees, the sine value, the y-coordinate of this intersection point, increases from 0 to 1. So sine of theta increases as the angle changes from 0 degrees to 90 degrees. Now when we graph, remember that we associate real numbers with radian measure, so I'll use radian measure on the graph. Let's look at Desmos. Let's graph y equals sine of x. You could put sine of theta instead. All right, now what's happening between theta equals 0 and theta equals pi over 2? The sine function is increasing. The sine values are increasing as the angle increases from 0 to pi over 2. We'll talk more about the graphs of sine and cosine later on, but if you remember the graph for y equals sine of x or y equals sine of theta, you'll remember that this graph goes up. The function increases in quadrant 1. And that's reflected in this pattern here. Now, what about cosine of theta? Take a look. This column for sine of theta, it almost seems like magic. You reverse this column to get the column for cosine of theta. And the reason is, the cofunction identities. Remember the cofunction identities. The cofunction identities said that cofunctions of complementary angles are equal. Cofunctions of complementary angles are equal. So that explained why, for example, sine of 30 degrees equals cosine of 60 degrees. Cofunctions of complementary angles are equal. They were both equal to 1/2. Well, going back to the table, look at these patterns. 0 degrees and 90 degrees, that's a complementary pair. They add up to 90 degrees. 30 degrees and 60 degrees, again, they add up to 90 degrees, a complementary pair. 45 degrees is its own complement. 45 degrees plus 45 degrees is 90 degrees. Well, so what? Take a look. Sine of 0 degrees equals cosine of 90 degrees. Sine of 30 degrees equals cosine of 60 degrees. Sine of 45 degrees equals cosine of 45 degrees. The sine and the cosine for 45 degrees are equal. Sine of 60 degrees equals cosine of 30 degrees, and sine of 90 degrees is cosine of 0 degrees. we reverse the sine column to get the cosine column. And that's because these pairs are complementary pairs and the cofunction identities. Now observe, the values for cosine of theta decrease. Why is that? Well, remember, cosine of theta corresponds to x-coordinates on the unit circle. And what's happening to the x-coordinate as we increase from 0 degrees to 90 degrees? Well, the x-coordinate, I'll erase these other pieces here. The x-coordinate here, x equals cosine of theta. The x-coordinate, as we go from 0 degrees to 90 degrees, the x-coordinate decreases from 1 down to 0. Cosine of 0 degrees is 1. Cosine decreases. Cosine of 90 degrees is 0. Also, if you remember the graph for y equals cosine of theta, the graph for y equals cosine of theta, if we look at theta equals 0 to theta equals pi over 2, the cosine graph goes down. Cosine decreases in quadrant 1. That helps explain why these values decrease from 1 down to 0. Okay, like I said before, it's very helpful to remember that sine of 30 degrees is 1/2, because then it's easy to remember that cosine of 30 degrees is the higher value, root 3 over 2. For 45 degrees, you may remember that these two values are equal. For the quadrantal angles, it's convenient to recognize the points on the unit circle. Over here, we have 1, 0. Over here, we have 0, 1. Know which is which is x, which is y. Okay, now what about tangent of theta? Tangent of theta is sine of theta over cosine of theta by the quotient identities. Tangent is also slope. We'll talk about that. Now numerically, we're going to use this quotient identity. Tangent of theta is sine of theta over cosine of theta. 0 over 1 is 0. This fraction over this fraction, the little 2's knock each other out. They basically cancel out. 1 over root 3 rationalizes to root 3 over 3. This number over itself is 1. Tangent of 45 degrees is 1. Root 3 over 2, all over 1/2. Again, the little 2's knock each other out. We have root 3. 1 over 0, that's undefined. Tangent of 90 degrees is undefined. Now remember, tangent is slope. It's the slope of the terminal side of a standard angle. So if we look up at the unit circle, erasing all of this, what happens as we go from 0 degrees to 90 degrees? What's happening to the slope? The slope, tangent of theta. The slope is 0 for the angle 0 degrees, and as we go through the quadrant up to 90 degrees, the slope is increasing. 0 slope, slightly positive. Tangent of 45 degrees is 1. Very positive. Slope can be a million, a billion. Tangent of 90 degrees, well, what's the slope of a vertical line? The slope of a vertical line is undefined. Tangent of 90 degrees is undefined. Increasing. 0. Remember, root 3 is about 1.7, so this is a bit higher than 1/2. 1. Root 3, again, is about 1.7, going towards infinity in a way. If you remember the graph for y equals tangent of theta, we actually have a VA here and a VA here. But if you look at quadrant 1, as theta goes from 0 degrees towards 90 degrees, or pi over 2 radians, you can see that the tangent values increase. In fact, they increase towards infinity. All right. Now, what about the reciprocal values? And what's the deal with these intersection points on the unit circle? We'll talk about those next time.